Hi everyone, thanks for coming to our talk. I'm Jacob Denson, and together with my group, Arthur, Benjamin, and Samantha, we're talking about the paper A Stationary Set Method for Estimating Oscillatory Integrals, which is a paper by Basu, Guo, Zhang, Zorin, Kranich. So we've put together a study guide for this paper, and we hope you'll take a look at it. So what is the main moral of this paper? Well, this paper discusses a category of two different problems and provides one link between these two problems. So let's introduce those two problems. The first genre of problems, they're called stationary set estimates. In a stationary set estimate, we're given a function phi from a set x to the real line, and the goal of a stationary set estimate is to upper bound the measure of a set of points which, when plugged into this function phi, are close to some fixed quantity mu for all in R. We think of this function phi as being stationary near a particular number mu if this set has large measure. So that's the problem in a stationary set estimate. Now there's another genre of problems. They come up all the time in harmonic analysis. They're called oscillatory integral estimates. And the goal of these estimates is to upper bound the quantity I given by integrating an oscillatory function with a phase given by the function phi. Now, in our talk, we'll fix x to have some real variable structure, which is necessarily to get the result we want, but there are many problems in which x is not necessarily a real variable structure. So here we'll be integrating over 0 into the d. You could also have some smooth phase in this integral. The method of this talk can be used to get results for those oscillatory integrals as well. Now, these problems have been seen as linked for quite a long time. For instance, if you can obtain oscillatory integral estimates, there are methods which enable you to convert those estimates into stationary set estimates. One such result is the Berry-Esseen theorem. It takes any upper bound for some oscillatory integral estimates and converts those into stationary set methods. The basic idea is to write the measure of your set. Let's call it S mu, which is the set in the stationary set estimate problem, and write it as the integral of the indicator function over that set, which we should be able to approximate by this integral multiplied by some smooth function, to which we can apply the Fourier transform. And we should be able to relate these to a certain family of oscillatory integral estimates. I'll make this more precise in the proper talk. But here we see that we can take any oscillatory integral bound and convert it to a bound for stationary sets. So that's been noticed as a method for quite a long time, since people had the Berrier-Seine theorem, which is used to prove the central limit theorem in probability theory. There are also ways to go the opposite direction, but actually not too many robust methods which enable you to take any stationary set bound and give you an oscillatory integral bound. There's a paper by Wenger and I forget the other co-authors. I'll have that in my notes for the proper talk so I don't forget. And this bounds takes any bound on the left-hand side and gives you a bound on the right-hand side, provided that phi is restricted to a convex function. So it doesn't really apply to a very robust family of estimates. However, the paper that we discussed today is able to do this, provided that phi is restricted to a semi-algebraic function, and we have a uniform bound on the complexity of that semi-algebraic function. If you're not too familiar with the terminology, this result will work if you're taking phi to be a piecewise function, such that on each piece you are a polynomial and you have uniform bounds on the degree of that polynomial. That's the main result of our paper today. Generally, converting the left-hand side to the right-hand side has been seen to be something that we should expect. For instance, there are many methods which allow you to get stationary set bounds and also allow you to get oscillatory integral estimates. They don't convert one to the other as like a black box, but it has been a heuristic in the literature for quite a while that any method that can solve one problem can probably be adapted to solve the other problem. For instance, this is mentioned, there's a paper by Stein, Sturm, and Fong from 1999. They obtain stationary set bounds, and they say the methods of this paper should be adapted, or it could be adapted, probably to get results on the right-hand side for oscillatory integral estimates. So this has been expected to be a result for a while, but there hasn't been many black box results. And the paper that we're discussing in our study guide is able to obtain such a result. So, what is that result? We're going to take a phase function Q, which is semi-algebraic, and it has bounded complexity. What that bound is not too important. This will just affect the implicit constants in our result. And given that result, if we take the oscillatory integral with Q as a phase, then the magnitude of this oscillatory integral is going to be upper bounded by bounds on the stationary set corresponding to that function Q. So given any stationary set bound, we can obtain an oscillatory integral bound. So we've got a successful result on that front. The proof uses a method in logic and algebraic geometry called O-minimality. We'll discuss that a little bit in the rest of the talk. Theorem 1 will be discussed by Ben after this part of the talk. Now, using this method, we can obviously get some interesting results. And the paper that we're discussing is able to use this result to get one interesting result. Theorem 2 says that if we take the following integral, which is an LQ integral of a family of oscillatory integrals given by this function p, where here p is a general degree k polynomial. So here c ranges over all possible coefficients for a polynomial with degree at most k, and when we're taking the oscillatory integral corresponding to that. And this theorem gives you a tight qk for which this integral is finite. So for q less than qk, this integral will be infinite. And so this is a tight bound. It only gives a tight bound for two-dimensional oscillatory integrals. The problem has already been solved for one-dimension oscillatory integrals. The reason for that is that standard results in oscillatory integral theory, stationary phase, are much more robust in the one-dimensional case. The problem has also been solved in all dimensions when k is equal to 2. Again, that's because quadratic polynomials have a particularly nice theory of stationary phase. They have non-degenerate stationary points. And so methods using this can be used to obtain tight convergence exponents for these types of integrals. But this result for two-dimensional oscillatory integrals gives you the result for k of arbitrary large size. We can use this result to get bounds on extension operators for an appropriate surface corresponding to kind of a general polynomial. And in fact, for the remainder of the talk, we'll denote this oscillatory integral by ek1. Just to remind ourselves that this is something a little bit like an extension operator. Again, we won't have time to talk about how this result implies restriction estimates, but that will be part of our study guide. So we'll be able to talk about that later in the week. This result also has results in number theory for Terry-type problems, counting the number of integer solutions to a system of polynomial equations. These types of estimates can be used to show those results. There's a section of our study guide which gives a expository look at how these results can be used to obtain those types of Terry, types of solutions to Terry's problem. That's in the study guide. We don't have time to talk about that today. That's all I had time to talk about. Next, Ben will discuss Theorem 1 and then discuss some ideas of the proof. And then afterwards, we'll discuss some ideas of the proof of Theorem 2.